Hey, Calc class. I hope your quiz went well this morning, and this is going to be your video on the next part of integration, which is called integration by substitution. I'm going to just go through some exercises that are found on page 337, and I'll go through a bunch of even ones, and hopefully you'll see how this works, and then you can try odd ones or retry these, which would be a good idea. To make sure that you understand it. So let's take a look. The first one, they give us this function here and they want us to integrate it. And if we look, it has two parts. And we could multiply this out 3 times and then multiply the 2x in so that we have a polynomial function and then integrate it term by term, which is what we normally were doing. However, if this were a 5th power, or 7th power, or 10th power, we wouldn't want to multiply that out. So what we do is we use what we call a dummy variable, which we usually use the letter u. It doesn't matter what letter you use. And we let that u equal one part of our function. In this case, I'm going to let it equal x squared minus 9. And if I replace that and I take the derivative of u, the derivative of u is a derivative of u with respect to x, du dx would equal 2x. That's just a simple power rule. And then if I multiply both sides by a dx, I'm getting this. So I'm going to take this out of my function and replace it with a du. And I'm going to take this out and replace it with a u. So now I have a much simpler function that I could take the integral of. I add a power to the 3 and divide by that new power, and that's my answer. Now that I did this, I want to substitute back what u was into this integrated function, and this will be my final answer right here. The next one is very similar, and a lot of times students ask me, well, how do I know what part of the function to make u equal to? And you just kind of have to experiment with it, but I think a good rule to go by, it's usually the ugliest part of the function. Or maybe it's inside of the ugliest part. And sometimes you'll try something and it won't work and you'll have to try something else. And that's okay. That happens sometimes. So this one, if I let u equal this in here, then the derivative of u with respect to x is going to be a negative 8x. Oh, and this is, I multiply both sides by dx, this is in my function. I replace this with a du. And then I replace this part with the u and raise this to the 1/3 power because it's a cube root. And then I could just do my normal integration. Add 1 to this, divide by that new exponent, flip it over and multiply it up top. And then once I'm all done, I replace the u with the thing that I originally said that it was equal to. And this would be our final answer. So, well, let's look at another one. And you can go back over these and watch this as many times or pause it and try it for yourself. Or you could pause it and say try number 5 or number 7. But let's look at number 10. This one here, I'm looking to make u this inside part here because I notice if I take the derivative of this, it's going to give me the outside part, but it doesn't give it to me exactly. And this is going to happen more and more. So the derivative of u, if I let u equal this inside part, is du dx equals a negative 3x squared. But that's not what I have in my function. I rewrote the function so this part here was together. And I want to replace both of these. It's easy to see that this will become a u to the 5th if I take this u and replace it for that 6 minus x to the 3rd. But this one, and different teachers do this differently, but I think this is the most logical way to do it. I solve for what I need and replace it. What I need is I multiply the dx up on the other side, and I divide it both sides by negative 3. So I solved for the part that I needed, which is the x squared dx. And now I'm going to replace that x squared dx with a du over negative 3, and I put that right here. Now, using the constant rule that if we have a function multiplied by a constant, we can move it out in front of the integral. I'm going to move a negative 1/3 out in front of this integral and then integrate this new, much easier function. by adding 1 to this, getting a 6, and dividing by that new exponent. And then I just cleaned it up, made it 18 on the bottom, and replaced u with what u originally was right here back into that function. And always plus c, because this function could have had a constant added to it. When we take the derivative of this, we get the integral. So take a look at that one again. They start to get a little bit more complicated. This one, it looks like if I make the u equal to this part on the bottom, I'm going to get my x to the third up top. However, I'm getting a 4x to the third. I don't know if you can see this or not. I'm getting a 4x to the third. I don't want a 4x to the third. I just want an x to the third dx. So I multiply both sides by dx, multiply that up over there, and then I divide both sides by 4, and I got this here. So now I'm going to replace this x to the third dx with a du over 4. So this gets replaced here. The u right here gets replaced with that, and that becomes a u squared on the bottom. Now it's a pretty easy function to integrate. I could move that u squared up top and move the 1/4 out front in front of the integral. Add a 1 to this and divide by the new number. So I have my answer really right there. Now we just have to clean it up. I'll make this a negative 1/4, bring the u back down to the bottom, and replace it with what it originally was up top. And so instead of calling this a u, I put the 1 plus x to the 4th back in, plus c. If it's not a definite integral, I have to put the plus c at the end. For number 26, again, I think the ugly part was inside of this cube root, so I let u equal that. Took the integral, du over dx equals 10x, multiplied the dx on both sides, and I'm looking for this x dx to replace. I have a x dx, but I had to divide both sides by 10 to make it be this x dx. And now I'm going to replace that x dx with a du over 10. And that's where I got this part right here. I replaced the 5x squared with the u, and now I have a u to 1/3. Now to make this nicer to integrate, I'll bring the 1/10 out front and bring the u to the 1/3 up as a u to the negative 1/3. Then go through my integration. Add 1 to this, so if I add a 3 over 3 to this, I get a 2/3. Divide by that new exponent, flip it over and multiply it up top, and I'm going to get a 3 over 20, and I'm going to replace this u with what u originally was, which is this 5x squared. And you could leave that exponent like that. You could multiply it in here sometimes if it makes it nicer. If not, you just leave it exactly like that, plus c. The last two I'm going to do for you have a trig function and an exponential function in it. Let's take a look. This one, I don't know how to take the integral of a sine 4x, but I do know how to take this integral of a sine u, so I made this part right here equal to u. If I took the derivative of that, I got du dx equals 4. And then I only have a dx in here. So I have to divide the 4 over, and I'm going to replace this dx with this in here. So that dx becomes a du over 4. So we put it right in there, and we have a much simpler integral. I took this 4, since it's on the bottom, moved it out front, and I got the integral of sine u du. If you forget, you could see page 282 for the integrals of the trig functions. All your integrals are there. I would get used to memorizing them, because when you go back in the fall, if you're taking Calc 2, your teacher will expect that you know these. So get used to referring to this page a lot and memorizing a lot of these. So let's see. What I do is I take the integral of this, which they say is a negative cosine of u, and that's my answer. Except for I want to replace the u with what it originally was. Instead of cosine of u, it's cosine of 4x plus c. This one looks really complicated, but it actually isn't. If we make u equal to tangent of x, the relationship between tangent and the secant squared is the derivative of the tangent is the secant squared. multiply the dx up in the other side, and what I have is I'm replacing this secant squared dx with a du, and that becomes this here. The tangent was the u, so I'm just making that now a u to the 1/2 since it's a square root. I'm going to add a 3 over 2, 1, which makes it a 3 over 2, and divide by that new number. So think about it, I'm adding a 2 over 2, which is 1. And 2 over 2 plus 1/2 is 3 over 2. And then I just replace the u with what it originally was. It was the tangent of x. So I'm going to put this back in for u plus z. The last problem here is has an e in it, and it looks kind of crazy. But if you break it down and you realize that if we let u equal this x squared plus 2x in here, du dx equals 2x plus 2. And if I factor out a 2, I'm having pretty much what I have over here. I have this and this, which I'm going to replace. But I don't have a 2 in there, so I divide the 2 on the other side. I solve for what I need. This is what I need to replace, so I solve for that, and I took this du over 2 and I replaced it with this x plus 1 dx. You could even rewrite it to put those together since it's all multiply. The e is raised to the u power because this I set equal to u. I'll take the 1/2, I'll move it out front, and I have an e to the u du. Well, if the derivative of e to the u is e to the u, then the integral of e to the u is e to the u. So this is going to be my answer, except that I'm going to take this u, which was this, and put it back into the function plus c, and that's my final answer. So try these exact problems again, and then just try all the odd ones on page 337 and do as many as you possibly can. We'll have a chat session on Wednesday at 11 o'clock, and I hope to see everybody there. We're only averaging about half the class, which is not good. Come prepared with questions, and we'll answer your questions on Wednesday, and we'll have another quiz next Monday. Only 2 to go, so I will see you on Wednesday. Bye-bye.